This lecture is part of a series of lectures on rings and modules and will be about colimits and exactness. So I'll start by quickly reviewing some examples of limits and colimits of modules and other things. So here are some limits, and here I'll put the corresponding colimits. So you remember a limit and a colimit depend on a sort of category parameterizing the things you're taking a limit over. So the simplest example might be a discrete category just consisting of some objects with the only morphisms being identity maps. And here you might want to take a limit of some objects m1, m2, m3 and so on. And here the limit of will just be the product m1 times m2 times m3 and so on. So the key point is that this has maps to all these objects and is universal with that property. So if you've got anything else mapping to m1, m2, m3 and so on, then it maps to the product. And the dual notion is the colimit. So if we've got modules m1, m2, m3 and so on, then the colimit is a universal thing that all the modules map to, which is just the direct sum. So all modules map to this, and if there's anything else that all the modules map to, then it factors through the direct sum. So these are products and coproducts, or direct sums. So the next example of a limit is a pullback. So this time the category, instead of being discrete, has three objects and a couple of morphisms other than the identities. And if we've got modules m and n mapping to a module t, the pullback, let me write the pullback in red so you can see it, will be m times over n over t, which is just the submodule of m times n, consisting of elements whose images are the same in t. So it consists of elements m, n in the product, such that m and n have the same image in t. And this also has a universal property. If you've got any other module mapping to m and n, it factors through this. And the corresponding colimit is called a push-out. So this time we've got modules m and n and a module t mapping to them. And what you do is you take the direct sum of m and n and you mod out by the image of t, mapping diagonally into these. And again, this has the usual universal property that if you've got any module with these mapping to it, there's a unique map like that. And another example of push-out we've had is just the tensor product of commutative rings. So if we've got rings R and S over a ring T, then the colimit is R tensor S over T. So the third and perhaps the most important example for this lecture of a colimit or limit is the kernel. So you remember, if we've got a morphism F and modules M and N, then we can introduce the second morphism 0, and the kernel would be the limit of this diagram. In other words, it consists of a module which is in fact the kernel of F mapping to M, and it makes these two, the two maps you obtain by composing this with F and 0 are both the same, and it's universal with that property. If we've got any module mapping to M, such that the composition with F and 0 are the same, then it factors through the kernel. Corresponding colimit is the co-kernel. Here we've got M mapping to N by two things M and N, and we want a universal object that N maps to, making the composition of these equal, and that's just N over the image of M under F, of course. Another example of a colimit is a so-called direct limit. So here the category might look like this. So it might be indexed by integers 0, 1, 2, 3, and so on. And this time we take modules m0 mapping to m1 mapping to m2. And the colimit will be a sort of universal module that these all map to. If these maps are, if mi is a submodule of mi plus 1, then m is just the union of these. In general, these maps need not be injective, and m will be slightly more complicated because you may need to take a quotient of the union. But the direct limit isn't too far from being a union. So we had an example of this in the previous lecture, where we take z over pz maps to z over p squared z maps to z over p cubed z, and so on. And we saw that the direct limit of this, which is essentially just a union, was an example of an injective module, was the injective envelope of z modulo pz, in fact. And last lecture we were discussing dualities, so you can ask, what is the dual of this direct limit? And that's not too difficult to work out, because the dual of z modulo pz is z modulo pz, and the dual of this is z modulo p squared z, z modulo p cubed z. So it looks a bit at first sight as if the dual of it is going to be just isomorphic to itself. But if you look carefully, all these maps between these go in the other direction. If you've got a map from A to B, you get a map from the dual of B to the dual of A. So in order to describe the limit, we don't take a direct limit of these. What we have to do is we need to take an element of the dual of this, and an element of the dual of this, and an element of the dual of this, and so on, which are all compatible. So we need to take an element of each of these that are compatible, in the sense that the image of the element here is the element there, and so on. And this is an example of an inverse limit, which is the a sort of dual notion of a direct limit. So one famous example of an inverse limit is the p-adic numbers, which is exactly what we've described here. We take these rings and just take the inverse limit of them. So it's a sort of universal ring such that all these map to it, and it just consists of elements of the product of these rings that are sort of compatible, in the sense that the image of this component will be this component, and so on. More generally, the dual of a direct limit will be an inverse limit. The dual of the inverse limit isn't quite the direct limit in general. The problem is that although elements of the direct limit do give you elements of the dual of the inverse limit, there can be extra elements of the dual of the inverse limit that you don't get like this. If you put a topology on the inverse limit, then you can quite often arrange for its dual to be the direct limit. But when you're putting topologies, you're not really doing algebra anymore. So another example of an inverse limit is the profinite completion of the integers. This is a slightly more complicated example of an inverse limit. It's really an inverse limit over a more complicated category. So what we do is we take z modulo 1z, which is not very exciting, it's just a trivial group, and then we take z modulo 2z maps to it, and z modulo 3z maps to it, but z modulo 6z maps to both of these, and z modulo 4z maps to that, and z modulo 12z maps to this, and here we've got z modulo 9z, so we get this huge, very complicated array of quotient groups. In general, we have z over nz mapping to z over mz whenever m divides n. So you can think of, we've got this huge infinite collection of quotients of z, and the inverse limit is going to be a universal thing mapping to all of them, and it's usually denoted by z hat, so it maps to all of these, and all these triangles commute. So the map to z modulo 6z followed by the map to z modulo 2z is the map from z hat to z modulo 2z. And you can see that z hat is given by just you take the product of all these groups and then just take the submodule of all elements whose components are compatible with these maps here. You can also describe this profinite completion in another way using the Chinese remainder theorem. What you notice is that z modulo nz is equal to z modulo p1 to the n1z times p z modulo p2 to the n2z, and so on, where this is the prime factorization of n. And this shows that z hat is equal to z2 times z3 times z5, and so on, where this is the p-adic integers, so it's the inverse limit of z modulo pz and z modulo p squared z, and so on, where p is 2 in this case and 3 in this case, and so on. So the profinite completion of the integers splits as a product like this. So this is just the Chinese remainder theorem. The profinite completion of the integers turns up a lot in number theory. You can use it to construct the adels. If you've done number theory, then one way of constructing the adels is to take the profinite completion of the integers and just multiply it by the reals. That gives you something called the finite adels over the integers. And if you then just tensor it over z with the rationals, that gives you the full ring of adels over the integers. The usual construction of adels in number theory uses things called restricted products, but it turns out to be equivalent to this construction here. Anyway, so that's some examples of inverse limits and colimits. So we now ask the following question: do colimits or limits preserve exactness? So in other words, suppose we've got various exact sequences, 0 goes to AI, goes to BI, goes to CI, goes to 0 for I indexed by the objects of some category. Then we can take a colimit or a limit of these, and we can ask, is 0 goes to the limit of the AI, goes to the limit of the BI, goes to the limit of the CI, goes to 0 exact? And the same thing for colimits. Does the colimit of these, is it exact? And the answer is sometimes. So it's true if the limit is a product or a direct sum. That's very easy to check. The direct sum of a couple of exact sequences is obviously giving you an exact sequence. There's one easy case when it does preserve some exactness, and this is that limits are left exact. So the limit is always exact on this bit, but the map from here to here is not necessarily surjective. And the reason for this is that left exactness is talking about kernels, and the point is that kernels are a limit. Here, AI is the kernel, and we see that AI is just the limit of this diagram. BI maps to CI, where this map is 0, and this is the map F. And the point is limits preserve limits. So in particular, since the kernel is a special sort of limit, limits always preserve kernels. And the reason for this is it's one of these things that's essentially a trivial piece of categorical bookkeeping. And you should really check it for yourself rather than watch my sketchy proof of it. So suppose you take the limit over some category I of the limit over some category j of some objects Fij. Well, this is just equal to a double limit over I times j of the elements Fij. And this is equal to the limit over j of the limit over I of Fij. So this is a very general thing, that limits always preserve left exactness. By the way, you remember that right adjoints also preserve left exactness, and since limits and right adjoints both preserve left exactness, you may wonder if there's some connection between limits and right adjoints. And in fact, you can check, if you like, that right adjoints are a special sort of limit. This is actually a special case. Any concept in category theory is a special case of any other concept in category theory. But anyway, so obviously the same thing applies, that colimits are going to preserve colimits, so in particular they will preserve co-kernels. So the question is, do limits preserve colimits? And vice versa, do colimits preserve limits? And the answer is, in general, they don't. And one simple way of seeing this is, we can just take a very simple example. Let's take the category I we're taking limits over to be just a category with 2 points. And let's take J to be another category with just 2 objects, because I'm feeling unimaginative. And we'll take limits in the category of sets rather than modules. And then the colimit in sets is disjoint union. And the limit of sets over this category is just a product of 2 sets. So we've got the following problem. We've got 4 sets, A, B, C and D. And we want to know, is the colimit of the limit of these sets equal to the limit of the colimit of these sets? So let's work out what this is. Well, the colimit of the limit means we first of all take the limit of these, which is a product, and then we take the colimit of this, which is the union of these. On the other hand, if we take the limit of the colimit, this means we're first taking a colimit, so we take the union of these, and then we take the product of that. And if you draw pictures of these are obviously not the same. For example, if I write A as a vertical line and C as another one, and B and D as horizontal lines, you can see that A times C union B times D is going to be this rectangle and this rectangle. It's just the product of A and B. Sorry, I mislabeled this. It should be the product of A and C union the product of B and D. On the other hand, if you look at this diagram, you get A, B, C, D. And this time we're taking the union of A and B times the union of C and D, and we actually get 4 bits. So the colimit of the limit is definitely smaller than the limit of the colimit, unless some of these are empty. In fact, you can see that the fact that colimits and limits don't commute isn't something pathological, it's something completely basic. For instance, if we write little a, little b, little c and little d for the size of these sets, the size of this is ac plus bd, and the size of this is a plus b times c plus d. And these two expressions are obviously not equal. You can't swap round addition and multiplication in this way. So there's absolutely no reason in general why limits of colimits should be colimits of limits. Actually, there is, however, one relation between colimits and limits. This page is probably going to be incomprehensible, so you can just skip it if you like. The point is, if you take a colimit over I of a limit over j of Fij and compare it with the limit over j of the colimit over I of Fij, although we've just seen these sets are not necessarily equal, you do notice that there is a natural map from this this collection to this collection. You can just map these 2 rectangles to these 2 rectangles. And in general, there's always a natural map from the colimit of the limit to the limit of the colimit, which need not be an isomorphism. And you can see this in several steps. First of all, there's a natural map from each Fij to the colimit over I of f I j, because there's always a map from objects to their colimit. Then you can take the limit of both sides of this, so you get a map from the limit over j of f I j to the limit over j of colimit over I of f I j. Just sort of taking limits of both sides. You can check that taking limits is a sort of functor, so we get a map like this. And now you can take the colimit over I of this, and all of these maps map to this, so by definition of a colimit, there's a map from this colimit to all these, to this thing here. So we get a natural map going in this way. That shows that colimits and limits don't commute for sets. Now we want to examine when they commute for modules. In particular, we're going to examine when colimits preserve exactness. So let's give an example where colimits do not preserve exactness of modules, and then we'll give an example of some sorts of colimits that do preserve exactness. So the colimit we're going to take is actually going to be a push-out. So I'm going to show that push-outs don't preserve colimits. Some sort of colimits do. We just mentioned earlier that direct sums, which are colimits, do preserve exactness. And now we need some exact sequences, and we'll use the standard counterexample to everything, which is the sequence 0 goes to z, goes to z, goes to z over 2z, goes to 0. And now we're going to, we need a colimit, so I need a couple more exact sequences, and I'm feeling really unoriginal, so I'll just take the same one over again. And now I want to take a co-product of, a push-out of each of these columns. So what I'm going to do is I'm going to have maps going like this. Notice that these maps here are going upwards and these ones are going downwards. So each of these three groups is a push-out diagram of this form. And this map is going to be multiplication by 2. So now I want to work out what are the colimits that we get down here. Well, the colimit of this means we take z plus c, which is this c plus this c, and then we quotient out by the image of this c, which is all multiples of 2 and 2, and this is isomorphic to z plus z over 2z, and this is going to be exactly the same, z plus c over 2z. And this one, I take this group plus this group modulo the image of this, and the image of this is actually 0, so I get z over 2 plus z over 2 again. And now we can check that this part of the diagram is indeed exact. However, this map here is not injective, because this map is just multiplication by 2, and it kills an element here. So colimits, or at least push-outs, which are a special sort of colimit, do not preserve exact sequences. Although they don't always preserve exact sequences, colimits quite often do. So what we're going to do is to show that direct limits do preserve exactness. So the simplest sort of direct limit is just the colimit over the positive integers. So we just take modules m1, m2, m3, and so on. And as we said, this isn't too far from taking their union. More generally, a direct limit will be a limit over a directed set. So a directed set is a poset such that given A and B in the set, we can find C with C greater than or equal to A and C greater than or equal to B. So an example of something that's not a poset is this sequence here, if we take A and B, then there's nothing that A and B both map to, so this is the category of a poset that's not a directed set. So this was the example of a push out, and as we saw, that doesn't preserve exactness. And what we're going to do is show that if we take a direct limit over a directed set, then this does preserve exactness. So the key point is that the direct limit of some modules mi over a directed set is equal to the disjoint union of the mi modulo the following equivalence relation, that m in mi is considered to be equivalent to n in mj if m equals n in some mk for k greater than or equal to I greater than or equal to j. That, when I say that, I mean the image of m and n in some mk. And the fact that the set is directed shows that this is actually an equivalence relation, and you can check that the colimit is in fact given by this union modulo the equivalence relation. The key point is that any element of the direct limit is represented by some mi in some big Mi. Notice that this fails for the colimit of these modules here. So if you have modules m and n and t, then the colimit is going to be m times n over the quotient of t, and not every element of this is represented by either an element of m or an element of n. There are some elements in here which you can only get by adding an element of m to an element of n. So this is the special property of colimits over directed sets, which is not true for colimits over arbitrary sets. And now we can show that colimits over directed sets are exact, so I'll just do it over the integers. So what happens is we've got all these exact sequences. 0 goes to A, 0 goes to A1, sorry, B, 0 goes to C, 0 goes to 0, and 0 goes to A1, goes to B1, goes to C1, goes to 0, and 0 goes to A2, goes to that, and we've got maps going like this. And we want to look at the sequence where we take the direct limit of the AI maps to the direct limit of the BI maps to the direct limit of the CI maps to 0. And we know that this is exact because taking direct limits is always right exact. And the problem is this injective? Well, let's pick some A in the direct limit of the AI with image 0 in the limit of the BI. Well, then A is represented by some AI in some A, in some big AI, by what we've just said. This is a property of direct limits over directed sets. And let's look at the image in BI, so it maps to some BI in BI, and this has to be 0 in the direct limit. So this must map to 0 in BJ for some j greater than or equal to I, because that's the condition for something to be 0 in the direct limit. And this means the image of AI in AJ maps to 0, so is 0 because the map from AJ to BJ is 0. But that means so AI has image 0 in some AJ, and by construction of the colimit, that means AI is 0 in the colimit. So we've proved that this map is actually injective, provided we're taking the colimit over a directed set. There is actually a generalization of directed sets. There's a more general concept called a filtered category. And colimits over filtered categories preserve exactness. So the proof of this is very similar to the proof for directed sets, except that I've got to tell you what a filtered category is. So a filtered category has the following properties. First of all, given A, B, we can find C such that there's a map from A to C and a map from B to C. So this is almost exactly the same as the condition we had for directed sets. However, we need a second condition. So given A and B with two maps between A and B, we can find C with a map from B to C, making such that these two compositions are equal. And you can now copy the proof that I gave that directed sets preserve colimits, and pretty much the same proof works for filtered categories. You need this extra condition to show that the relation you try and write down is an equivalence relation. So we've seen some examples where you don't preserve exactness if this condition is missed out. I'll just finish by giving an example to show if you omit this condition, then exactness still isn't preserved by taking colimits. And the example we have uses our usual exact sequence. This is multiplication by 2. And let's take another copy of it as usual. So here I'm going to take my category to have two objects and two arrows. So here the two arrows are going to be multiplication by 2 and multiplication by 0. And now I work out what the colimits are. And the colimit of this is just z modulo 2z. The colimit of this is z modulo 2z. And the colimit of this is z modulo 2z. And this is multiplication by 2. And you can see it, this bit is exact, but that this map here is not injective. So we see that we do actually need both of these conditions for a filtered category in order to preserve exactness, because if we drop either of these conditions, we've found counterexamples where the colimit of exact sequences need not be exact. Okay, that's enough about colimits. Next lecture will be about whether limits preserve exact sequences.